Okay, so I'm going to do a quick example of setting up a CROD type of problem in HyperMesh. So I was going to do the same one as my first Nastran, that one, but I think I have some videos that already do that, and so I'll do a Torsion one because actually the next homework will involve doing some Torsion ones, okay? So the problem that we're actually going to solve is one of the homework problems. This problem 3, it just has this thin open-walled section, and it gives us the dimensions. Well, okay, in this one it's actually a little bit of a design problem. So it wants you to find the maximum torque. Okay, so what we will actually do is something a little different. Since we don't know the torque, I will put like a unit torque. Like in this case, I will probably put like 1,000 pound-inches on here, see what the stresses are, and then since this is all linear elastic, that'll just allow me to scale the results. So if the stress is half of the allowable, then I know I can actually double the applied torque. Okay, so but basically it's an exercise in really about setting up the problem in hypermesh. So we'll talk about the how we're going to calculate J and C, which we need for the CROD element, okay? All right. So it's aluminum, right? And we know that. Okay, so we start hyper mesh. So make sure it's hyper mesh 2022. Have the right version, and also make sure it's hyper mesh, not hyperworks. Even though it says hyperworks up here, your screen should look like this. If it looks more like some more, how would I say, pictorially interesting icons, a little bigger, you probably run HyperWorks, not HyperMesh. Now, whenever you start, you're going to be given this user profile. This is what allows you to pick what sort of solver, processor, you want to pre-process for. Now, in this class, we are going to use OptiStruct, so I'm going to click OptiStruct and hit OK. All right, so like I said, we are going to use a very simple finite element model. It's going to be a single CROD element, and we use the parameters that are specified in the problem. Now, the units are imperial units, so we will use length as inches, force is going to be pounds, which means that Young's modulus and stress have to be in PSI, and moments or torques need to be in pound-inches, not pound-feet. So you have to be careful about making sure your numbers being typed in are consistent, right? There's no units in finite elements, but the numbers have to be consistent, okay? So the first thing we're going to do is, like I stated in class, we're going to go through the fundamental steps in creating the cards needed for the model. So we are going to first make the material, then I will make the property card, then I will make the mesh, apply the boundary conditions, and go on from there. So first thing I'm going to do, like I said, I normally use this window here. I right click in this area and I hit create material. So we're going to make a linear elastic isotropic material that is card image mat 1. Just like we talked about in class, we can rename it. We'll call it aluminum 6061 if you want. And we'll put in Young's modulus. So Young's modulus for aluminum in imperial units is 10e to the 6th. And we'll put in Poisson's ratio of 0.3. Okay? Remember, you only have to put 2 of the 3 elastic constants. It'll automatically calculate G. You can see actually if you hover over. I believe that is the... No, that's not. I don't know what that is. But it'll calculate the correct G being, what is it? E over 2 1 plus nu, I think, right? Okay, so we have the material. It's going to have a bluish color if we choose to color by that. Now next, we are going to define the property card for the CROD element. So if you remember, if we define a property card, I'm going to right click again and hit property. And now we will have to change this card image. The default is a shell property, but we're not going to use that. We're going to change it. You can see here to a bunch of options, but we want to do PROD because we're using the property for a rod element. It always gives you this warning. You can ignore that. We'll change the material. We'll pick in here the already defined aluminum material. Like I said before in class, you can go back and assign it later, but I find it easier just to do this. And you'll see we'll have to put in the properties A, J, and C. That's what we need, all right? So let's talk about how we're going to do that. So here's the geometry here. It's a thin wall, opened section. So we're going to use that theory, right? So if you go back to the summary sheet of how we calculate those parameters, you can see actually the three last columns are the ones we need for a PROD card, the area, J, and C. And if we look at an open thin-walled section, it's really the same as if we just like opened it up, right? So J is T squared times H, T cubed times H over 3, where H is this distance of the midline path, if you will. Area is just H times T, and C is just going to be T, and that's going to be the correct values we should put in. So let's calculate those. So you can use a calculator. It's pretty simple, but you know, I like CoCalc. So here's CoCalc. I already put in the dimensions here for the cross section. A is 5, B is 5, and T is 1/16. So from that, we can calculate H. H for that path, right? If you look at it, it's going to be 2 times A plus B, right? So we're going to say 2 times A plus B. And hit return. Well, we'll do it this way. J, let's use capital J. Capital J is H times T cubed over 3. And C is just T, actually. And so we'll calculate those. We need to show them, so let's just do that. We'll just do show H, show J, and show C, and there are the values. So, well, actually, I don't need H. I need the area. Oh, I'm sorry, I need the area. Duh, I just calculate the area. Let's do that. The area is the path H times T. And we don't really care about H, actually. We really care about A. So there we go. So there's our values. A is 0.93. I'm going to just... Actually, I wonder if I can cut and paste those suckers in. I might be able to do that. So I can copy and paste that into this property card. That's the area. Let's see if it works. It does. All right. And this is J. So put that in here. And then finally, the value for C. And we'll call it, you know, channel property or something. Okay, so there we go. And that's ready to go. So I've got the material, I've got the property card. So now I'm in a position to actually make my mesh. So if we look at the problem statement, the total length of this section... Oh, okay. I'm sorry. So if you look at the problem again, so I'll have to change this a little bit. It wants me to determine the angle of twist per unit length. So there's a couple ways we could do that. We could make the section just have a length of 1 unit. It's going to look a little weird, but we could do that. Just for the heck of it, I am going to do this, and I'm going to make a length. I'm going to arbitrarily pick it to be 10 inches. And in doing so, I can just divide by the length to get the angle of twist per unit length as well as the torque and all those sorts of things. Okay, so let's imagine it's you want to think it will give you the length is 10. Okay, so we're going to create the nodes. So all that stuff is going to be under the geometry. So you click the little geometry radio button down here. Now we have a bunch of things that allow us to construct lots of types of geometries. This is really simple. So all we need to do is just type in the node coordinates. So I'm going to click on node, and now you can see I get this window here. I know I tried to zoom in as much as possible so you could see it. I know the print is small, but whenever you get these, look through these different options. These are various ways of constructing nodes, and some of them are really useful. So we are going to just straight up type in the node coordinates, but one can also select points. I don't know what this one does actually. I've never used that one. I know one can generate a set of point nodes on a line. Also between two nodes, at intersections of lines and whatnot. So those are all very useful, but we're going to use the boring, just type in the coordinates. The first one we're going to put in is at the origin, 0, 0, 0. So I type in 0, 0, 0, and I hit create, and there it is. And now we'll make it so that the z-axis is the torsional axis, right? So the next node would be at 0, 0, 10, if you will. Okay, and I'll create that. And I think it's off the screen. It's somewhere. Where? Oh, I know why it is. I have to rotate it so you can see it. So if I rotate the axes a little bit. There they are. Okay, so here's the z-axis, right? Okay, so now we're pretty much ready to make the element. So it's a one-dimensional element, so we're going to go into hit the 1D radio button here, which will allow us to construct a variety of one-dimensional elements. In this case, we are going to pick a rod element, which is, a truss. Now let me talk a little bit about this. This is something I didn't really discuss in class because I was going so fast. But so Altair Hypermesh is made, or it's designed to support a variety of finite element softwares. So everybody has a different name for their truss element, okay? And very often there's several types of truss elements. So the way Hypermesh chose to deal with this is it calls everything that's kind of like a truss, it calls them this general category rods. And likewise, anything that's sort of a beam is a bar, rigids. But if you go to element types, you'll see you have this sort of mapping. And now on the left are the terms that Hypermesh refers to it. And then it says, okay, if you pick a mass element in Hypermesh, I'm going to make this type of OptiStruct or Nastran element. So these values change depending upon what software you're using. If you select ANSYS in the user profile, you will get different words here because it will use the ANSYS class. So we're going to use rod elements, and you can see here the rod element defaults to a C-weld element, which is a type of Nastran or OptiStruct element. We want to change that to be a C-rod. So if I click on this field, here are the things that it could be, and C-rod's right here, so I'm going to pick that. So that means when I make a rod element, it's going to make a C-rod element. Again, if you forget to do that, it'll make C-weld elements. You can change those, but let's get it right to begin with. It makes it easier. So then I'm going to hit return. So if you don't do this and you make a bunch of C-weld elements, I believe you can go into this same window, select those elements here, and then update them. But we're going to do it right to start with. And so we hit return, and now we're ready to go. So we're going to create the rod element. So we pick rods. You can see here the element type is now set to C-rod because we did that correctly. The property is not assigned. It's just property 1. So let's make sure we use our channel property. So I click on that, and then click on channel property. And we're going to create. So again, if you want to change properties, if you want to change types, you can use update here and update an existing element, but we're going to just create it. So I'm going to pick this node and this node, and there it is. It created a CROD element as we want. You can see it also created this component here, and it gives it a name. A component is like a collector bin for, like, you can think of it like a part. So you can have a bunch of elements, maybe even different element sections, right? So sometimes these can be quite large. So we can give this a better name if you want. We can rename it. So I right click on it, rename it, and let's call it C channel. Although here it's not going to be hard to keep track of it. But if you have millions of elements, it might behoove you to make well-named components so you know here's the shell elements for the deck of the aircraft. Here are the C-bar elements for the stringers and so on, right? But anyway, so you don't have to do that, but we do that. All right, and like I said before, you can, this is also very useful, you can change how it's shaded by different ways. So you can change this by component, and now you can see the element is blue, which matches the color for the component. We can shade it by property, and when I do that, you can see now it's yellow because it matches channel property. And you can also shade it by material, and there it is. This matches the material. So if you have multiple materials, multiple parameters, this is an easy way to see which properties and materials are assigned to which elements, okay? Usually I just have this at component. All right, so there you go. There's our element. We should probably save this file. I'm going to save this. Let's put it, well, I don't know where to put it. Let's put it into, it's always tough finding stuff on here. Well, let's just do it in documents. I'll just create a new, we'll just do it in documents. It'll be a mess, but whatever. So I'm going to call this example. Okay? So there we go. So it's going to put all the output files in documents and whatnot. All right, so here we go. We've got the element defined. Now we have to apply the boundary conditions, the torque as well as the fixation, okay? Now, I think they fixed this bug, but let me just make this statement. Usually, so these big nodes here that look like tennis balls or something like that, or golf balls, those are actually temporary nodes. And sometimes it gets a little confusing when you go to assign boundary conditions. So I believe they fixed this, but I tend to delete those before I move forward. Now when you delete those, they're temporary nodes. The actual node for the CROD element will still exist underneath it, but it'll no longer look like a tennis ball. So if I go here under geometry, temp nodes, and then clear all, or you can select them, but I'm going to clear all. They go away. Now there actually is a node still here and here. It's the actual Nastran grid point, okay? All right, so now we're going to create a the constraint. We're going to fix this point here at all 6 degrees of freedom. So all boundary conditions, constraints, loads, forces, pressures, are under this analysis radio button. So I click on that, and you can see we got a bunch of things here you can set up. Vectors, different types of coordinate systems. We talked a little bit about that. Moments, which are torques, point forces, pressures. You can set up equations that define distributed forces, load steps, whatnot. So let's first do the constraints. So that's going to be various types of SPCs. So I hit constraints. You can see there's actually different load types here you can use. We haven't talked about any of these except SPC. We'll use an SPC. We're going to pick the node here. So that's highlighted. And we're just going to pick it, that node there. Now, this area here is where you define the value. So we're going to have all 6 degrees of freedom and set them equal to 0. If you only want to set certain degrees of freedom, uncheck these or check these appropriately, and you can also set them to non-zero values like 0.1 or something like that, and you can do that by changing them here. We will not do that. We're going to keep all 6 degrees of freedom fixed, and we're going to fix them to 0. So we go create, and there you go. And you can see here, it shows the fixed degrees of freedom, all 6 of them. Also, it created something over here on the left-hand side, a load collector. And if I break that open, it needs to keep all the loads and the SPCs in collectors. Now, when we talked in class about that set identification number that's used to kind of group boundary conditions to be applied for different load steps, right? That's what's going on here. So, it really doesn't matter. You can rename this. We're only going to have one set of boundary conditions, only one load step. But if you have multiple ones, again, it's nice to be able and rename those. You can also create those. If you right-click in here, you can create load collector. Okay, so if you want to, I'll create one for forces, for torques, just for the heck of it, right? So, and then I'll rename this one to be SBCs, right? There you go. Okay? So, also, what I should notice, now that we have 2 load collectors, I'm going to create the force now. I have to make sure that the collector I want to have those put into is what we call active. So, you can see this is bold, so it actually is active. But, if you wanted to change it, you can highlight the collector and then right-click, and you'll see there is a make current. So you click make current. Now SPCs is bold. So that means I can create a force, I can create anything. It'll put it in there. I mean, just because it's named SPC, it's not smart enough to know, like, hey, don't put forces or torques in there, right? But we want to make the torque and put it into here. So I'm going to right-click on that and make that current. All right, so now let's apply the torque onto this right-hand side node. So let's return out of here. A torque, like I said before, is a moment. So here's the panel again. You can see the load type is a moment. And we're going to make a moment around the z-axis at this node. And let's use a value of 1,000, okay? So first, we're going to pick that node. So I click on nodes and I select the node. Now, we're going to change the magnitude to 1,000. So that is 1,000 pound-inches, and it's going to be a right-handed sense around the vector I define. So if you wanted to go the other way, you'd put it in minus 1,000, right? Now, these here allow you to pick the vector that the moment is about, okay? Now, you can pick components of a vector, or actually there's a lot of ways to do it. If you click this little thing here, you'll see there's different ways to do it. So one of the ways is just picking an axis. And for us, that's the easiest, right? So it's going to be around the x-axis. So I'm just going to click x-axis. And so now you can see this is a moment around, I'm sorry. I said x-axis. The z-axis. I click it. What I say doesn't normally mean what I do. Okay, so the z-axis, right? So this is going to put the 1,000 moment around the z-axis. It's going to go in a right-handed sense around here. And so I can create, right? And there you can see what happens is it creates the moment, shows the magnitude, and it uses that convention where there's like 2 arrows for a moment to differentiate it from a force. So you can see there's a right-handed moment around this. If you put your thumb in the direction of the arrow and curl your right-hand fingers, that's the way the moment is. You can see it's red because it's in the torque load collector, right? And there you go. Okay. So we have the forces, the boundary conditions, the properties, the materials all set. The last thing we have to do is define the load step. So this is the thing in the executive section that says, hey, we're going to do a linear elastic solve. We're going to use these SPCs, these forces, and these sets, okay? So again, you can actually do it through here as a load step. Or you can also right-click in here and create load step, I believe, right? Where is it? Load step, there it is. Okay, so we're making a load step, and then we can give it a name. Load step 1's probably fine, again, but often you'll have multiple load steps, so we'll just say twist, or torque, right? Whatever. And, okay, wait, let's click on that. Now, here's the things in the card. So, these are the different options that go into that executive case summary. I should probably, I wonder if I can do that real quick. We've seen the cards. If I can just open this up. Oh, I know where I can do it. I know where I can do it. I can do it through let's do sorry about this. I should have had this up already. Let's load this up again because I know it's in here. This might help again. This might be a little easier to understand. So remember, we talked about the executive load control section, right? Where it says what solver we use, and then the SPCs and the loads and the outputs and all that sort of stuff. So that's what's going on here. You can see SPC, load, and then also output. Where's the output? Oh, I think it's even down further. There's lots of options here, but no. Where's output? Oh, there it is. Here's subcase option, so it's down here. The output is down here. Okay. Output, right? So, you know, like in here where we wanted to output all the displacements, all the SPC forces, all the von Mises and everything, right? That's what it does. Okay. So let's do this, right? So we're going to change the analysis type. This is the solver, so we're not going to use generic. We're going to do a linear elastic. This is solver 101. So linear static. Pick linear static up here. All right. Now, what SPCs are we going to use? Well, click on this, and you can see it wants you to pick a particular load collector. So we're going to pick the one that has the SPCs we want to use, which is called SPCs. And also the same thing for the load. So we want to pick the load collector here that has the loads we want to use in this load step. In this case, it's going to be torque. So we're going to click on here and then pick torque. And so it's like a lot of steps, and you might not appreciate it now. And well, I might be wrong as well. But I think knowing those cards and the different things that go into the simple input files helps you navigate through this interface, because they're all, the workflow through this interface is based on that, you know, the things that you referenced. So there you go. That's good. Let's change the output. Now for these simple problems, we're actually going to do something a little different with the output. We're going to write the output to a text file, because there's only going to be one element, and it's just going to be easier to look at the results, okay? Normally, we'd also write them to a binary file that you can look at a post processor and make pretty pictures and all that sort of stuff. But we're going to make sure we can write everything to a text file that we can actually read, okay? So what are the things that we want to output? Well, let's output the displacements. Let's output the element forces. So that's going to tell me the torques and the axial loads and all that stuff. Let's also output the stresses. You can do the strains too, but let's just do the stresses. Now, each one of those has sub options in here. The one that we really want to make sure we get correct is the format. So the format tells you how do you want to write those results out. So for us, we want to write them into this opti file. You can see it, if I can't move my cursor over to it, but it's the third option down, right? So we click on here and we change it to opti. We'll do that for all these. So format, opti, and you'll see why. Format. So that'll put it into a format that's easy to read in a text file, okay? So we're good. So we're good. There we go. So we've got the load case defined. We've got everything defined. Let's just save this. And now we're ready to run the analysis. So I hope I did this all correct. So we can now just run this through analysis and then click the OptiStruct. So this is going to execute the current input file into OptiStruct. Here's the input file. It's in my documents folder. It's called example.fem. That's actually going to be the ASCII file that looks like the one we looked at in class. Here are some options. It doesn't really matter, but we're not actually going to do an optimization. We're just going to do an analysis. So you can click that to be analysis. It doesn't matter for what we're going to do, but we can do that. And that's pretty much it. So we're going to do optistruct, and this will start it running, I think. And here is the run. This gives you the output of the run. It goes very quickly. It's a very simple problem. It didn't get any errors. If it did, it would give you errors here and here, but it seems like it worked. And we're done. Okay? We're done. So, oops. Did I get rid of that window? No, it's still here. Actually, in general, if you also want to look at the thing visually, I think you can also hit results. And if you hit results, it'll bring up the HyperMesh post processor, which is called HyperView. So I know you can't see it because it's out of the screen, but it's this, right? And like I said, for this one, it's kind of boring because it's just a line. But we'll talk more about this later on. But you can then change this to like shade by like different types of things. Like if you want to look at the stresses, right? There you go. That's the element stresses, right? And well, there's 0, but that's because these are the axial stresses, and then we just put a torque on here. So that's expected, right? We'll use this more when we get to more complicated problems with more elements, and with one element we'll just look at the text file. Okay. All right. Well, that is a lot of stuff. So let's stop here. I'm going to pause the video, and then I'll do a second video where we look at the results. Okay.